we are learning digital ramp type voltmeter. Okay, and the way it works, if I tell you that in the form of a story, is that it basically has a counter and the output of the counter goes to a DAC. Say there are 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. So this goes to the input of a DAC, digital to analog converter. Okay, so you see that this is a 8-bit binary number. Call it n for number, okay, or call it NB, that means a binary number, and the output from the DAC is a voltage, call it VR, okay, which is same as some constant multiplied by this number. Okay, and okay, let me just call this constant. Okay, this is a constant, so NB I can call it anything. So let me just call it VREF. Okay, so the constant I'm giving a name VREF, which stands for reference voltage. Okay, so this stands for now if I connect the clock to the counter, so what will happen? The counter will increment each time it gets edge here, and therefore the VR value of VR will also increase. So this increases like this, like a staircase function. This is how VR increases. Now you think of it that we are generating voltages of different level, like this is 0 volt, this is equal to how much? This is VR. Okay, VR, this is 2 VR, this is 3 VR, and so on. And we will ask a series of questions that there is a input voltage that we want to measure. Okay, there is an unknown input voltage. So let me write that here. Vi, this is unknown. Now we will ask a series of questions. Is Vi greater than 0? If the answer is yes, then we will ask again, is Vi, is the input greater than 1 VR? If the answer is again yes, then we will ask, is the input greater than 2 VR? If the answer is again yes, we will ask, is the input greater than 3 VR? And so on. Okay, so we will keep asking, is it greater than 1 VR, 2 VR, 3 VR, 4 VR, 5 VR, and say at some point we will get the answer no. Say greater than 1 VR, yes. Greater than 2 VR, yes. Greater than 3 VR, yes. Greater than 4 VR, no. The answer is no. If the answer is no, so that means the unknown voltage is greater than 3 VR but less than 4 VR. So it is somewhere between 3 VR and 4 VR. So that will be my estimate or my measurement of the unknown input voltage. So we will keep asking this question, is it greater than 1 unit, is it greater than 2 unit, and so on. So let me also draw analogous situation which you have definitely seen in shops, in grocery. So when we are measuring say an unknown weight with a balance, okay, with a normal balance which possibly look like this. Okay, this has two pans. This is one pan, this is another pan, and in one pan we will put the unknown weight. Let this be an unknown weight. Wx, and the way we measure it is by putting what do you call, I do not know, these small blocks of standard weights. I do not know what it is called, like 1 kg, 2 kg. So these small reference weights are there. So we will put them one by one and see whether, so initially, you know, this was empty, so this was initially heavy, the pointer was here, and then we will put these weights one by one, put weights one by one. Okay, 1 kg, is the pointer shifting its position after when I put 1 kg? Say no. Okay, that means this is heavier than 1 kg. So then put another 1 kg block. Now we have 2 kg here. Then let's ask, is the pointer shifting its position? No. Okay, that means it's heavier than 2 kg. So then we put another. And now if the pointer changes its side, oh, definitely that means this weight is less than 3 kg but greater than 2 kg. Okay. So question, is Wx greater than 1 kg? Answer is yes. Say the answer is yes. Then ask, is Wx greater than 2 kg? Say once again yes. Then you ask again, is Wx greater than 3 kg? Say no. So this will imply Wx is definitely therefore between 3 kg and 2 kg. This is how we measure, right? And the same thing we do in case of a digital ramp type voltmeter. So this is the unknown. Okay, so we need something like this balance to compare two weights, not weights, two voltages. So and that is going to be a comparator. Say if this is plus, this is minus. Here I will give reference voltages which will increase slowly. Okay, so that I will get from this. So this tells me whether, so this is, here I get the answer, is Vi input greater than Vr? If yes, if the answer is yes, okay, then what I will do, I will increment this counter. Okay, if Vi is greater than Vr, if yes, then the counter will increment, and if it is no, then you know this value will go down. The moment Vr becomes higher than Vi, this value will become low, and therefore the output of this AND gate will be low or 0, so the counter will stop. Okay, so let me also connect the clock. Okay, so this is how it works, as simple as that. Now let us ask some interesting questions. Okay, so let us ask, say, okay, before that let me just tell you that this output, you know, this is Vref multiplied by this binary number NB, and we may have generally a control, okay, by which you can change the value of Vref. I should, to be technically correct, let me just call it V resolution. This is also, to be technically correct, I should give the name resolution. Okay, so this also is resolution. Okay, so with this is a control to this DAC with which we can change this constant. That's one thing. Okay, now let's ask question or example. Say the V resolution is equal to 10 millivolt, and say that we have a 10-bit counter. Okay, now the question is, what is the range of voltage that we can measure? What is the range of voltage that we can measure? So what is the range of this input Vi that we can measure? Do you know the answer? It's very simple. Okay, so the answer is, so 10-bit counter means the value of the counter can go up to 2 to the power 10 or 2 to the power 10 minus 1, which is 1024. Okay, so 1024 is the maximum, not 1024, 1024 minus 1, which means 1023. So the counter can take value between 0, 1, 2, 3, 4 up to 1023. This is the range of the value that this counter can take. So the maximum value is 1023. Now then what will be the maximum value of VR? So maximum value of VR will definitely then be 1023 multiplied by V resolution, which is 10 millivolt. Okay, so then this will be 10230 millivolt, and this is the voltage, maximum voltage that we can measure with this arrangement. So Vi, the maximum value of Vi is this. If the value of Vi is above this, say it is, so this is how much? This is 1, so this is equal to 10.23 volt. If the value of Vi is, let's take this is equal to 15 volt, okay, then we can never measure it, because this value will never be more than 10 millivolt, sorry 10 volt. So the comparator output will never come to 0. Okay, so VR will never go above Vi. Okay, so the counter will never stop. Yeah, it will definitely stop after 1023, or it will get reset. Okay, so this crossing, this is never possible. You see, this is this is VR. So there are up to 1023 steps. Okay, so this is like 10 point something volt, 10.23 volt. But if Vi is here 15 volt, if this is Vi, right, so they will not cross each other ever. This measurement will not work. So this is the maximum input voltage we can measure. Maximum Vi measurable. Answer. So this is the answer. Now let's ask another interesting question. Okay, say if the frequency of the clock generator is equal to say 1 megahertz, and if Vi, the input voltage, is equal to say 5 volt, okay, then how long do we need to measure this voltage? Okay, so this is the next question we can ask. Okay, so Vi is 5 volt. Okay, so if I draw, so this is 5 volt level. Vi is equal to 5 volt, and V reference or VR, call it not V reference, VR, which is this digital ramp. This digital ramp, okay, which I am calling VR. So VR is increasing like this. So this is VR, or the digital ramp, stepped ramp. Okay, so this is increasing like this, and each time it is increasing by how much? V resolution. So this value is V resolution. Each time it is increasing by this amount. Okay, and this time is 1 clock cycle. So every clock cycle is increasing this voltage VR by V resolution. Now then the question is, how long will it take for this to go beyond Vi? Because at that moment when this goes above Vi here, then the comparator output here will be low, the counter will stop, and we can stop the process of measurement, because we now know that is the value of, so this is the value of Vi. Okay, so how long will it take? So the time required, or say the number of cycles required, is equal to this voltage Vi divided by this height of each step, V resolution. Okay, and in our case this is equal to 5 volt and the V resolution is 10 millivolt. Okay, so this will be 500. So 500 cycles. So we need 500 cycles, 1, 2, 3, 4, so on, 500 cycles for this measurement to be completed. Okay, now 500 cycles is same as 500 multiplied by t second, where t is the time period of clock. Okay, so this amount from, so here this is the time period of the clock. Okay, and how much is this? So this is 500. I can write this 500 by f is the frequency of the clock, 1 over time period. So this will be equal to, I can write 500. Let me not write the unit here, instead I write here, this is how much? 1 megahertz. So 1 megahertz. Okay, so you can now calculate what the value is. This will be I think 500 microsecond. Is it? Check. 500 microsecond, I think. Check the calculation. So this is the amount of time it will need. Okay, now let me ask another question. What is the resolution of the measurement, or of the voltmeter, of this voltmeter? So this is the next question, right? Okay, so we are taking a lot of examples to help you understand this. So now we are going to calculate the resolution of this voltmeter. Okay, so before that, let me just remind you what resolution is. What do we mean by resolution? If I have, say, a voltmeter which has markings like this: 1 millivolt, 2 millivolt, 3 millivolt, etc., and it has a pointer definitely. So the pointer, this is the pointer. So the pointer can be here, here, also in between, but it has only these markings. So if I just rely on these markings, then I can say I can measure the voltage as whether 3 millivolt, 2 millivolt. But it is difficult to say whether it is 2.9 or 2.8 because those markings are not present. Okay, so therefore I can say, if I just rely on these markings, the resolution of this meter, this is an analog meter with a pointer. So the resolution of this meter, I can estimate this to be 1 millivolt because the gap between two successive markings is 1 millivolt. Okay, so resolution for this is equal to 1 millivolt. Similarly, take an example of a digital voltmeter which has a display like this. Okay, so it has a display and the symbol V appears here. Okay, so now so it can display what? It can display 001, 002, so on up to 999 volt, volt, volt. Okay, so it cannot display 1.5 because that is not possible. Okay, according to this scheme. So for this digital meter, we will say the reading is resolution is again 1 volt. Okay, so for this resolution is equal to 1 volt for this meter, right? Now let's go back to our scheme, ramp type voltmeter. So where we have this counter 10 bit, that's what we have chosen, 10 bit counter, and from this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, from this we have a DAC, V resolution is equal to 10 millivolt. So the output from this is some number n times 10 millivolt. N is this number. Okay, let me call this NB. This is this number. Okay, so we are comparing VI, unknown VI, with reference voltages as 0 volt, then V resolution, then 2V resolution, and so on. So which is same as 0, then V resolution is 10 millivolt, okay, then 20 millivolt, and so on. So we can only compare, is the input greater than 0? If yes, is the input greater than 10? If yes, if the input greater than 20? And somewhere, say if we find that the input is above 10 millivolt, below 20 millivolt, so we will say, okay, the input is 10 millivolt, something like that. But we can never say whether it is 15 millivolt, 16 millivolt, 14 millivolt, no, because we are not comparing with those levels. So we are comparing with in the steps of 10 millivolt, right? So therefore we will say the resolution of measurement is 10 millivolt. Okay, so we can only say that something like Vi. So we can only say something like say Vi is less than 70 millivolt but greater than say 60 millivolt. Okay, we can never say if Vi is equal to 63 millivolt or say or 64 millivolt, etc. So the steps that we are comparing with, that is what is called the resolution, is 10 millivolt, right? So the answer is therefore resolution is equal to 10 millivolt. Now I hope you possibly have understood why did I call this voltage, why did I give the name V resolution, because this is essentially is the resolution of our measurement, right? That's why I gave the name V resolution. Okay, so please understand what do you mean by resolution. Okay, so this question is done. Okay, now let us take another question. So another question. So we have seen that the time required to measure 5 volt input was how much it was? Let me check. Here 5 volt input, the time required was 500 microsecond. Okay, was 500 microsecond. So it seems that the required time depends on the input voltage, right? Why? Because you see, I mean, the scheme of measurement is this. So this is our input voltage. Okay, call this is Vi equal to 5 volt, and the reference voltage is increasing like this. So this is VR, digital ramp, and this is the time required. Okay, this is the time required for the measurement, which is same as the time required for VR to become larger than Vi. Now, if say Vi is this much, say Vi equal to 4 volt, then the time required will be this much, right? And this is smaller. Now if I have Vi larger, then the time required will be something like this, which is even larger. So larger the value of the input voltage is, it will take more time for me to measure the input, because it will take more time for the this digital ramp to cross the input, right? So it seems that the time required depends on the input voltage. Now then I can ask, what is the maximum possible time required? What is the maximum possible time required? So this is the question. So do you know the answer? It's easy. You see, the maximum time will be required when we are measuring a very high input, because if the input is higher and higher, it takes more and more time. Okay, so what is the maximum voltage we can measure? The maximum Vi that we can measure is how much? This is what we have seen in example 1. Okay, let's go back. So the maximum, say here we maximum value of Vi that we can measure is this 10.23 volt, right? So this is 10.23 volt. Now to measure this voltage, how many clocks do I need? To measure 10.23 volt, we need how many clocks? How many cycles? 10.23 volt divided by V resolution, this many cycles, which is same as, so I can write this as 10.230 millivolt and V resolution is 10 millivolt. Okay, this many cycles, which is same as 1023 cycles. Okay, so the 1023 cycles is same as 1023 multiplied by time period of 1 clock cycle, or 1023 divided by the frequency, which is same as 1023 divided by, I think this was 1 megahertz, right? If this is 1 megahertz, then this will come out to be 1023 microseconds. That's the answer. Okay, so in terms of so we can say in terms of number of clock cycles, the maximum number of clock cycles required is same as, you see, the highest number that this counter can represent. 1023 is the number, the maximum number that this counter can represent, and that is also the maximum number of cycles that we may need to measure our input voltage. Okay, so if we have n bit counter, let me write it in a different page. So if we have an 8-bit counter, okay, so this essentially means I also will use 8-bit DAC. Okay, so because the output of the counter goes to the DAC, so normally if this is 8-bit, then I'll also use 8-bit DAC, or if this is 10-bit, I'll use a 10-bit DAC normally. Okay, let me call this n in general, n-bit counter, which means also n-bit DAC. Okay, normally. So if we have an n-bit counter, then max voltage measurable is how much? 2 to the power n. This is the number, the maximum number that the counter can represent, or maybe a -1 if you are starting from 0. Okay, so this multiplied by V resolution. This is the maximum voltage measurable, and maximum time required is same as 2 to the power n minus 1 cycles. Okay, just think about it once again on your own. So this is an important thing we can see easily. This is a normal situation, but do not memorize these formulas. Please do not. Okay, because I may change the scheme slightly in exam or in practice, where these formulas will not be true exactly, but you just understand the idea, so that even if I tweak the circuit, even if I tweak the scheme slightly, you can come up with correct answer. Do not apply the formula blindly, okay? Then your answer will be wrong. Okay. Now this is okay, fine, this is a nice result. Now let's come to another interesting topic, which is called successive approximation type voltmeter. Okay. This is a slight modification of digital ramp type voltmeter. Okay. So let us see what is the change. Let me divide this page into halves. This side I will write digital ramp type voltmeter. Here we will talk about successive approximation type voltmeter. In this, how do we measure an unknown voltage? We compare the unknown voltage with a known voltage which is increasing with time. Okay, so we ask the questions: is the input greater than 0? Is the input greater than 1 V resolution? Is the input greater than twice the V resolution? And so on. Okay, so we ask questions like, first we ask, is Vi greater than first 0 volt? Then we ask, is Vi greater than V resolution? Then we ask, is Vi greater than 2 V resolution? And this way we will continue up to how much? What is the last value we compare with? That is 2 to the power n times V resolution. Okay. So the last value that we will compare is Vi greater than 2 to the power n minus 1 times V resolution, where n is the number of bits of the counter or DAC. And that is why we in general need 2 to the power n minus 1 cycles. Each cycle give me the answer to one such question. Okay? And if the Vi input is very high, we will ask all these questions. We have to ask all these questions. So we have to ask this many questions, which will take a long time. Now, an intelligent guy will not do this in this way if he wants to save some time. So what he can do, an intelligent guy can do, so he can ask directly. Let me take an example. Something like, let me take n is equal to 4, okay, which implies 2 to the power n minus 1. This is equal to how much? 15. Okay. So if that is the case, that means we have to, in this side, we have to ask questions like, is it greater than 0, is it greater than 1 v resolution, up to is it greater than 15 v resolution. So total 16 questions we have to ask. But an intelligent guy will ask the questions in this way. So question 1, is Vi greater than, say, 8 times V resolution? This is the first question. Okay, so I am not asking is it greater than 0. No, I am asking directly, is it greater than 8 times V resolution? Okay, and the answer can be either yes or the answer can be no. If the answer is, say, yes, Vi is greater than 8 V resolution, then the next question that we will ask is this: is Vi greater than 12 V resolution? Let me just write V res to save space. Okay, so this is the next question. And if the answer is no, then my question will be, then my second question will be, is Vi greater than 4 V resolution? Right? So this is the second question, which I will ask depending on the answer of the first question. Now, say if the answer is yes, and say again here I can have two possibilities, yes and no. If the answer is yes, then I will ask, what should I ask? So I know it is greater than 12 V resolution. So now I will ask, is Vi greater than, say, something like 14 V res? And if the answer is no, then I will ask, is Vi input, so I know this is not greater than 12 V resolution, so definitely it is less than 12 V resolution. But here I have found that it is greater than 8 V resolution. So if I come here, then I definitely know the input voltage is between 8 V resolution and 12 V resolution. So I will ask, therefore, is it greater than 10 V resolution? Because 10 is somewhere in between 8 and 12. Okay, so I will ask this question. Okay, so you see, the way I am asking these questions is this: if I draw, this is voltage, and the voltage that we can measure is between 0 and 15 V resolution. So 0, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we know that this is the measurable range. For Vi. So Vi can lie only within this range. If it lies above this, we cannot measure. Okay? So that is invalid input. So the way we measure it is, we directly compare first the input, whether this lies above this center point, above it or below it. Okay? So this is the, so if asked, is it on this side or is it on this side? Okay, you may some of you may think be thinking that actually this is not half. Half of 15 is 7.5. So why I have chosen 8? Why not 7? Okay, that is we are not going to bother about that so much right now. That may be too much of detail at this point. Let's assume 8 is approximately half of 15. Okay, so we directly ask, is Vi on this side? Or is Vi on this side? If it is on this side, then next time we will ask, is it here? That means in this part, or is it here? Suppose after the next comparison, I find that it is greater than 4 Vi, then I will ask, is it here or is it here? So this way, you see, we are narrowing the possible range of the unknown input every time by a factor of half. Okay, so initially so at the beginning I know definitely the input is somewhere in between this to this. After one comparison, I can definitely say, okay, the input is within this. After two comparison, I know the input is within this. Now the range is even halved. After 3 comparison, I know, say, possibilities here. Okay, so this way I am narrowing the range of the input. Okay, I am approximating the value, unknown value of the input every time in I should say more and more accurately. So initially I can say, if I know nothing about the input, then I can say the input is between 0 and 15 volt. That is the crudest answer I can give. Next time I can say, okay, the input is between, say, maybe between 0 and 8 volt. So I have a better estimate or better approximation of the input. Next time I will make it even smaller, this range, and I will say, okay, the input is somewhere between 4 and 8. So I am approximating the unknown in a more and more accurate manner, and that is why this is called a successive approximation type measurement. Okay, so I am narrowing the range every time by a factor of 2 or half, like this, then this, then this, so on. Okay, so I hope now you know why this type of measurement is called successive approximation. Successive means more and more, better and better approximation of the input voltage. Okay, that's what we are doing. Now let me ask a question. What is the time required to measure an input Vi with successive, let me write in short, successive approximation type voltmeter? So how many clock cycles do I need? Okay, say in this case I have 15 possible values of input, and every time I narrow the range by a factor of 2. So this means so number of clock cycles required is, I can write this as log base 2 times the range, or let me call it number of possible values. Okay, so number of possible values for the input. Why log 2? Because every time I half the range by a factor of 2, so you can ask how many such measurement, how many such comparisons should I do, or how many such questions should I ask. Okay, so those of you who have done some courses in computer science, some programming, some data structure, you will find the similarity of this method with, you know, binary search. If you are not familiar with this term, no problem. If you are familiar with this term, you may correlate this with that. So this is the number of questions that I need, and so this I can write, this is equal to log 2. Okay, and how many possible values do we have? This is equal to 2 to the power n, 0 to 2 to the power n minus 1. So for 4 bit, this is 15, not 15, 16, because we start from 0, so total 16. And so this is equal to log 2 to the power n, this is nothing but n. So this is the number of clock cycles that we may need for successive approximation type measurement. But in case of digital ramp type, we would have required 2 to the power n minus 1 clock cycles. Okay. So let me go back to the previous slide where I have this comparison and just write a small conclusion that maximum clock or maximum cycles required is 2 to the power n, or maybe a minus 1, maybe no, not, because we are counting 0 as well. Okay, we are comparing starting from value of 0. Okay, so this is the maximum number of cycles required. And now if you divide this by the frequency of the clock, you will get it in terms of second or time. Here maximum clock cycles required is equal to n, where n is the, what is n? N is the number of the bits in the counter or in the DSC. So let me write, this is n bit. Okay, this is also n bit. N bit successive approximation voltmeter. Both are n bit, so both will give me the same range of measurement, same resolution of measurement. Okay, but this is slower, this is faster. Let me just conclude. Same range and same resolution accuracy. So both this type will have same range, same resolution. Okay, but this is slower. This type is slower, this type is faster, but same accuracy, same range, because we are using same number of bits. Okay, thank you.